Hi, everyone. Thanks for inviting me. My name is Ahmet, by the way. I'm a researcher at Cohere Labs, formerly Cohere for AI, and Cohere. Yeah, thanks for having me here. I'm really, interested in modular or decentralized approaches. When I get invitation, I thought like, what can I talk? Because I'm both fan of all these different approaches, starting from adapters, hypernetworks, MOEs, or merging. But also I worked on all of these topics more or less. But based on some of our recent works, I wanted to talk about model merging at scale. So here the title of my presentation: Model Merging at Scale, as one of the most underrated tools in LLM training toolbox. So one disclaimer: this is actually from a tweet that one of my colleagues' tweet. I just slightly changed the wording. So underrated doesn't mean that it is unpopular. I'm sure this is maybe one of the most popular tool currently, but I wanted to use this phrasing as underrated because I think still it is very underrated when you are building a frontier language models or multimodal language models. Because at the very large scale, I still don't see much application of model merging. But as opposed to this trend or this status, at Cohere and Cohere Labs, we actually using model merging as really a tool to build frontier LLMs. Then I will talk a little bit on those. I'm sure all of you people know what is model merging, but just for completeness, I started with that. Model merging, basically, you combine the parameters of two or more neural networks into single neural networks. I mean, most standard way, architecture should be the same, but there are also ways to do different architecture, different models with different architecture to merge them. But the general idea, you have different capabilities in different models, and you want to compose these capabilities into one model, right? So there are lots of different merging techniques, so I'm not definitely going into all these techniques. But the simplest way is linear parameter averaging. You interpolate multiple models with different weights for their parameters. So why you may want to do model merging? That is the first question, right? Of course, the first advantage of model merging is resource optimization. So you think that you have 5 different models. Instead of deploying five of them or sort of doing inference over 5 of them, when you merge all into one, you just need to do inference into one. So this is the first, I think, the simplest advantage of model merging. Similarly, you don't need to use all of them in the memory, so you just use one model in the memory. So in that sense, it is quite different than model ensemble. But in terms of, so you probably want model merging not only because resource efficiency, but also there are some other inherent advantages of model merging. One is this independent training or decentralized training, right? Maybe you have, I will give some more concrete examples, but you have multiple expertise, multiple task languages, and you want to train them separately with the maximum parallelization, and then you want to reuse them. So this is potentially one of the inherent advantage. Or maybe you also don't want to train them, but you can just use one of the model that has been trained for somebody else. So actually reusable, repurposable neural networks, also in that context, merging is really effective. Another thing, not only for independent training, but even if you have all the resources that you can train one single model, but still there are lots of optimization challenges when you have like a frontier scale large language models, right? You have lots of different tasks that you want to optimize for. You may want to have lots of different languages that you may want to optimize for. Then there are lots of tricks that you need to do in the data ablations, mixture ablations. So it might be super costly. So instead of doing those, you may want to train different models and compose these expertise. Actually, this is the part that I wanted to highlight a bit in our works. So these are the some works that I am briefly going to touch. So IA Expanse and IA Vision are multilingual LLMs. One is multimodal, very recent. And finally, I will also touch a bit Command A, which is our frontier LLM, that we probably the first frontier scale LLM that used merging in the full scale. So let's start with IA Expanse. IA Expanse is a model family that has both 8 billion and 32 billion parameter scale models. And the main highlight for IA Expanse model was optimized for 23 languages. So the main target was multilingual expertise. So here, I will highlight the merging as a tool for combining capabilities across languages. So why I wanted to start with IA Expanse, because multilingual optimization is actually quite hard. Because you have lots of different languages from different scripts, from different linguistic structures, from different language families, and this actually presents a unique multitask challenge, right? So to be able to solve this in one single training run, probably you need to have really balanced data mixture, but this is also not super easy, because you want to balance different languages, but also you have some data sets only exist in some languages. Let's say you want to have, of course, mathematical capabilities, but potentially you only have mathematical capability data sets in English, but you also want to sort of transfer this capability to, I don't know, Turkish. That's why if you really want to do in one training run, you potentially need to run lots of different ablations to find both the balance across languages, but also balance across tasks. So it's quite difficult. And yeah, requires lots of fine-tuning. Also, even if you think you find the right balance, still potentially you will have uneven improvement or uneven performance across different languages, right? So this is IA 23.8b, the model family that is we deployed. I mean, we trained before IA Expanse models. Here we have quite a good improvement for the baseline. At the time, it was a state-of-the-art comparison, but in English, as you can see, the improvement was not there. So we were gaining a lot for multiple languages, but not in English. I think this is also, together with multiple factors, this was also about this balancing across languages, because as we push towards the multilinguality, probably we heard some English performance there. So when we start IA Expanse project, just after IA 23, we were thinking, like, can we use merging across language specialized models to reduce this data mix ablations, aggregate computational cost? So we have actually a work published before IA Expanse. There we sort of experimented merging language specific models into one model. So these are not, so I think there was in total 6 languages: English, French, Spanish, Hindi, Arabic, and Russian. In one experimental setup, we mix all of them, only one model, train them. This is a mix. In another experiment, we only use English, French, and Spanish separate language models. We merge these three language models. And in another experiment, we merge 7 different language-specific monolingual language models. And here we see, this, I'm explaining this because to give some reference about what might be important for this kind of situation. So as you can see, merging actually outperforms mixing in both scenarios. But there is also a trick here. When you merge similar language models, your performance is a bit more. So actually, there is also interference in merging. So starting from this observation, for the IA Expanse, we moved from like careful data mixture ablations to iterative model merging. So here, we of course don't have only 7 languages, we have 23 languages. We wanted to have sufficiently diverse checkpoints so that we can leverage this model merging advantages, but also we don't want to have 23 different language models that potentially lead still an interference. Also, we wanted to leverage cross-lingual transfer, right? Just like in this case, if the languages are similar, probably we will have a better performance. So with this kind of requirements, what we did, we split data into language families so that we have less specific language models that we train separately, and these languages that we put together are close to each other so that we have potentially maximum cross-lingual transfer. Together with that, to increase robustness, we also add some languages to all language models, to all sort of clusters here, to increase robustness there. And we did this in multiple stages, which I will show, to also to improve merging as we go. So this is the general training sort of framework. You can disregard this part. This arbitrage is basically the SFT part. The technique that we name it for synthetic data generation was arbitrage, but merging was central piece of all this IA expanse post-training recipe. So what we did, as I said, we cluster languages based on language families, separately train them in SFT stage, which leads n number of different SFT model. We also has some languages like Spanish, English, French, shared across all the clusters. Then we merge them. Then we do another round of training, which in this case could be offline DPO, offline preference training, again across clusters. Then we merge them, and we go on this. I think it was 4 iterations. So there are a couple of important things here. One is iteration, because I will also touch upon this in the last phase in the command A, but after you merge, you may not be still in the optimal place in the lost landscape. Probably all the different SFT or DPO models or separate models that you trained learn separate information, you merge them, probably you are in between some lost point in the landscape between all these separate models. Training more, doing much more iteration, actually sort of polish this, polish the position in the lost landscape. And when you combine this with DPO and also online DPO, you get actually the best performance. So this is the results that we get from IA expanse merging experiments. So you can start comparing from here, SFT with our SFT with multilingual arbitrage idea. And this is win rates again against Gemma 2. It was somewhat around 48. Then with only merging without any iteration, improved somewhat 5 points for the win rates. And when we combine this merging iteratively with preference training, this time we get also much higher performance improvement. So here, of course, there are two factors. One, preference training, it improves already, but we did preference training with merging. That's the main thing for the IA expanse. So this is also for reference to the previous generation IA models. In there, we were losing from English, right? Because we had this uneven advantages when we pushed towards the multilinguality. But in the case of IA expanse, because we now have separately trained models, potentially leveraging the performance much better for different languages, even for English, we had actually quite a good performance. So actually, this sort of merging mitigates hurting some performance in sort of high resource languages. Yeah, that was IA expanse. For after IA expanse, we wanted to build a multilingual language model, which named IA Vision. We recently released. Paper is not released yet. The screenshot I showed from the paper gonna be released in few weeks, I think. But here we actually did something I would say quite novel. This time merging across modalities. So this is just like a recap about this sort of multimodal language models, late fusion. Basically, you have an LLM, probably completely post-trained, including preference training, and you have another vision encoder. You want to fuse them to a multimodal language model, right? So you have a connector, but basically you do mostly multimodal training. But as you do multimodal training, there is always this problem. You may lose performance from the text capabilities, because the focus of this training now, kind of improving the multimodal understanding, but I mean, you may want to add some text data, but still you will probably lose text-only capabilities. Here, actually, you can disregard IA Vision. I will explain IA Vision later, but these are some baseline models that we want to understand even beginning of the project. whether these multimodal language models are really losing performance in text-only domain. And this is a win rates across multiple languages. So each model compared to its own original LLM. For example, Qwen 2.5 VL here compared to Qwen 2.5 LLM. And as you can see, all the multimodal LLMs here significantly lose text-only performance. But from the beginning, when we were developing IO Vision, we wanted to combine both state-of-the-art multimodal capabilities and state-of-the-art text-only capabilities. So we actually did not want to lose too much from text-only capabilities. But this is our first set of experiments for the IO Vision. When we did multimodal training with, of course, diverse set of multimodal and multilingual data, and compared with the baseline, our original LLM, which was IXpand, this is the win rate. So we were losing about 20%. This was a really high drop, right? So in general, if you look at the literature, different labs add lots of text data to recover textual performance. But actually, that is also quite tricky because if you add the same all these language models are, as I said, potentially fully post-trained. So, but you start again from the SFT, so you undo some of the preference training operation, right? This is first problem. Secondly, you have a set of text-only data, very high-quality text-only data that you use for LLM post-training. So potentially, you want to use all of them when you are training LLM, but then you jump to multimodal training. To recover some text performance, you want to add this time, again, text-only data. But then there is this potential of overfitting because you are reintroducing data multiple times, right? So in the best scenario, if you want to recover with text mixture in the multimodal training, you need to find another data that your model probably did not see before, and you still need to do lots of different data ablations, how much text data that you need to add to text training, the multimodal training. But instead, in IO Vision, actually, we did something much more simpler, in terms of practical point of view, but slightly bit more novel, I would say. We first did full multimodal training, then we merged original LLM, which is completely did not see any multimodal information, right? Just LLM, with the LLM and decoder of the multimodal language model. So we test a couple of different merging methods, but we basically use linear interpolation. And after we did the merging, these are the results. So first, of course, our main motivation was recovering the text performance, right? So it was somewhat about like a 20% drop. And after we did the merging, simple linear merging with the two models, now the IO Vision compared to the IXpand, which is the original LLM, was 46 win rate. So it was almost in the same ballpark compared to the original LLM. So that was pretty interesting because, even with the start of the project, we did not really expect that much of a high jump. And we were thinking maybe we first need to do multimodal merging, then we need to do also some more training with the text mixture. But only multimodal merging actually kind of recovered most of the text performance. But even more interesting, after we did multimodal merging, which the main motivation was text recovery, then the multimodal performance itself also improved. Because if you think about multimodal performance, this is especially important in the merging context because of the compositionality between task and languages. You ask a model about an image, then you get a text generation, right? If your model has a better textual capability, your multimodal performance also potentially better. I think this is the improvement that we see with the multimodal merging was coming from this. And this is quite a significant level here. So all these evaluations were for win rates, which is much easier to see this sort of improvement. But also we wanted to have a complete story and also look at the academic benchmarks here. So this is win rates that I show with a different merging fraction. So we did actually 0.4 merging. 0.4 meaning the weight of the multimodal LLM. And this in the right side you see the academic benchmarks. And this actually you see quite the same story, although the smaller degree. Of course, the text performance improves quite a bit because you are putting more text weights into the mixture. But even for the academic benchmarks, your multilingual academic benchmarks, your multimodal performance improves from, I think, 50 or 48 to 50, 51. That was actually quite surprising for us. And combined with the multimodal and text performance here, because that was the main purpose of all this exploration, we wanted to have like a sort of Pareto optimal area for the both multimodal and text performance, and this actually kind of allow us to be in that region. Okay, in the last piece, I would like to briefly talk about Comment A, Cohere's frontier model, which we full-scale use merging across lots of different task expertise. So here, like we see merging works across languages, and in the IA vision we see merging works across modalities. But when you go to like super large scale, which is like a 111 billion language model, and also targeted for multiple different expertise, including some enterprise needs and general purpose capabilities, you have much more domain of expertise, right? You want to combine. And in the same, just like in IA Expanse, you have lots of data mixture problem, interference problem, and commonly these problems solved in other research lab with the sequential training. So, for example, if you look at Llama 3, I think they train with order of different tasks, mathematics or multilinguality, then combine all the tasks all together and do training in multiple order. But then you have ordering problem. And when you do the sequential training, potentially you also have forgetting problem. And each of these different expertise may actually require different sort of algorithmic algorithmic approach, and you are losing this sort of flexibility if you do one like a chain of training. Instead, for the Comment A, we asked like, how can we enable this decentralized asynchronous training for different model capabilities and join and optimize all of them at that. So in that sense, as I said, Comment A is the actually first large-scale attempt to combine all these kind of merging ideas in a very large scale. So the general training recipe is quite similar with IA Expanse, with some really novel and new additions. Starting from, so this is the general recipe. Again, there is a multi-step merging. You can see here. From the SFT, we have one merging operation, and for the preference training, we have another merging operation. So this is also iterative. But one new thing from diverging from IA Expanse, actually starting point, also not the base LLM, but this time starting point is another supervised fine-tune instruct model. So I will touch upon on this point a bit, but this was quite important. Then, in the first stage, we train multiple different experts for, in this time, is quite a lot actually, and 7. And why this is important, not because of only a large number, but all these expertise are quite different from each other, right? You have safety expert and you have long context expert. So actually quite likely that in the same data mixture, you may introduce lots of interference. But if you do in this separate training, you have much less interference if you do merging well. After the first SFT training, we merge all of them, called SFT soup model here. And then, again, we are branching for 7 times with the different expertise for the preference training. So the nice thing about this overall schema, for each expert, you can try different SFT methods, you can try different preference training methods, right? Maybe for long context, you may just use offline RL, but for multilingual expert, you may want to use offline RL and online RL in different manner. And for math and reasoning expert, you may want to use verifiable RL from verifiable reward, right? So this gives you maximum flexibility of algorithmic components. And the last phase, this was also diverging from IExpense, which was pretty important for Command A, was polishing. Because, as I said, after all the merging, because there are quite a lot of number of expert model here, you might end up somewhere suboptimal, and you want to do a little bit iteration to move this your model to the optimal place. And here we experimented with both SFT and different preference training algorithms. So these are some plots for showing the before-after merging operation. In the left side, you see this is aggregated. 0 meaning the best expert performance matched with the final checkpoint. Minus points are your final checkpoint are slightly bit performing slightly bit lower than your best expert. If it is the plus, your final checkpoint actually performs slightly bit higher than the best expert for the corresponding task. But the main point here is merging preserves most of the expert performance, including the top performance here. So it's between 0 and minus 2.5 is the main average for the expert performance. And if you look at the separate expertise here, expert domains, actually for many domains like multilingual, RAG, or general, you have almost the top expert performance in your final checkpoint. Actually, all this leads this model to be very competitive with other frontier models, right? Because, of course, these are benchmarks, does not directly correspond all the expertise, but the combination of all the expert models actually lead this model to be excelling in academic benchmarks, agentic workflows, or code, or multilingual. So there are some learnings from Command A. Also, linear merging, similar to IExpense and IAVision, was extremely efficient. And in this case, for the Command A, it was even more efficient because when you have larger model, linear merging seems to be much more smoother than more sophisticated approaches. Second one is I think quite important, the kind of explaining why we started from the instruct checkpoint, is consistency. So maybe if you just start from the base checkpoint, you may reach the better optimality for the particular expert, but somewhat consistency between expert models are quite important, and starting from a SFT checkpoint, you actually allow the models to be more consistent between each other. The third point here is model merging is coarse operation, which meaning, of course, there is no guarantee that you will end up in the Pareto optimal point. So that's why this polishing, even before polishing, after each merging, you may want to do small steps of updates, SFTs, to have like an optimal performance for the merge checkpoint itself. And this is sort of negative, but I think this is important when we are talking about the merging. Merging is cheap in a way, but it's expensive in other way, because you have this time sweep of merging weights, right? You need to do lots of evaluation. So I especially wanted to put that because this is one really nice future research area, in my opinion, like this from the evaluation search and some other like maybe smart algorithms to do less iteration for finding the best merge checkpoint would be pretty important for the large scale. Yeah, and overall takeaways from all these three models, I think one thing which is pretty clear for us was merging is really a tool in super large scale frontier model development. So it's not maybe it doesn't need to be a central point, but it's definitely within the toolbox. Just like how you have SFT or how you have any RL algorithm, merging is also one of them. You can treat as a method that you can use within all the framework. It enables decentralized training. This helps organizational point of view, first of all. It enables composing different capabilities. In the extreme version, modalities. And it's kind of enable us to avoid large data mix sweeps. Another important thing is here is like never a single step operation. I think we always see better performance when we iteratively merge models. And the last point, I think this is also a really nice research area for the future project, is very important what you are merging together. If the checkpoints are super different from each other, it's another problem. If they are super similar to each other, it's also another problem, right? So there is another balance in this checkpoint mixture that you want to merge there. Yeah. Thanks, all of you. Yeah. Oh, of course, I should give a short shout out to all my colleagues from Cohere and Cohere Labs. I mean, this is a large amount of work for all these three different models.
Thanks for the talk. I have a question about Command A. Have you maybe run on a smaller scale experiments, ablation experiments, in terms of, okay, how does performance compare when we take the full data set and essentially train a model on that versus, taking these expert models and merging them?
Actually, I showed Command A sort of framework and results, but the same sort of recipe applied also 7B command, R7B, and that was also performing really well. Actually, we first did, of course, R7B, then the Command A to validate the framework. So in small scale, it also works same way.
Sorry. I'm curious about, have you done maybe the concrete ablation experiment of training on the full data set, like the joint data set essentially of all of these tasks, versus training experts and merging them, and how that compares in terms of performance?
I don't have the results, but I'm sure those experiments definitely, because this is the main baseline, right? You first want to combine all the data, do one run, and combine with the merge checkpoint. I'm sure that we had, of course, leverage from the merging, but I don't have results to show you.
I had a question on Command A, actually. I mean, it's a twofold question. Just to grasp the scale of the SFT versus the pre-training. So kind of the twofold question is, do you tune all the parameters at that point? And second, what is the amount of work in the pre-training of the model versus, the SFT phase?
So pre-training is beyond all this context, actually. So, I mean, of course,
but just to give a sense of, like, I don't know, is it like 1% of the watts, dollar, whatever is the unit, or is it like 10%, or is it?
To be honest, I don't have that sort of comparison for pre-training run and SFT run, but I can surely say that SFT or all the post-training runs are much more smaller scale than pre-training.
Like a thousands would be a good scale, for example?
I don't know.
Okay. And here you tune all the parameters?
Yeah. For SFT, this is not like a separate, like a LoRa or another adapter approach, but all the parameters are tuned for all the experts.
I would like to ask if, like, when you merge all the models, like, does model architecture matters a lot? Since, like, we all know, like, some dense model merging might be straightforward, but some MOE models or like larger models that might like have multiple layers and multiple activations. Does that change the recipe, or does it remains the same? Thank you.
In these models that I am showing, all of these models are dense models, and architecture are also exactly the same. Only, like, I mean, still architecture is exactly the same, but only minor, I think, note here, this multi-model merging, because we merge only part of the model here, right? This kind of shows that merging can go beyond the full same architecture models, but I think this is something also needs to be explored even more. I know there are works to model merging for MOEs, but I'm not sure, like, the trade-off when you compare dense model merging to sparse model merging, to be honest.
Thank you so much for the talk. If you go back to that architecture slide you're showing.
Which one? For which model?
Where you're showing the instruction checkpoint.
Okay.
Yeah. How do you determine the readiness of the instruction tune checkpoint, and what metrics are you using to evaluate that?
Mm-hmm. I mean, of course, there is a bunch of evaluation that we do here.
But at Cohere, yeah.
But before the evaluation, because this is not the final point that model reached, right? More important, there is like to provide the consistency, you need to have a sort of data that the model should see and then branch to the experts. Because, like, for example, compared to the drug expert to long context expert, there is quite a bit of difference in data set representations even. If you look at the data sets are quite different, how the prompts and instruction and completions are formatted. The first instruction fine-tuning step is especially important for this having consistency that model won't go diverge with the separate style of data.
I have the feeling that model merging is very counterintuitive. Maybe you have a better understanding of like what happens when you merge two models in a multilingual context. What actually makes it that it's actually working?
So maybe I didn't understand the first part. Can you repeat?
So my point is, I think model merging is very counterintuitive, and maybe you have an intuition on what's actually happening when we merge two models for two languages, and it's actually working.
Yeah, I mean, probably there is much more hypothesis around that. But if you think about the normal gradient optimization, what you do in standard one run, you have like you are trying to go down through the loss landscape, right? But in the model merging case, this time you have separate models. Let's say two different languages. Of course, when you combine them, there are some works that shows directionality of gradient can be different. It's leading the interference normally, right? When you have separate training, each language is in this case going in own route. When you merge, you try to find somewhere in between that works for both the models. Actually, that's why there is no guarantee that you may not really find the correct local optima. That's why you may want to do a little bit more training. But I think that is the main reason for that. But if you are asking a specific case, I agree that's quite counterintuitive. Especially, I was super surprised this multi-model merging, to be completely fair. But after I think more, after of course I see the results. So here there is this image encoder, and we did not even update the image encoder except the connector. And these are all in the input space. And the model output space is actually the same. So when we merge the original LLM with the multi-model trained LLM, actually these are in the same output, operating in the same output space in a degree. Since we did not touch the input space, it's kind of intuitive in that sense to get a performance there.
And maybe a question from me related to this. Do you guys treat the vocabularies differently, like in terms of the embedding layers? I can see how if you're basically diverging for different languages, you might have to basically, did you have to worry about treating the embedding layers differently, or you just merge them like
in IOVision, actually we did not update the embedding layer, but this is not because of merging, this is because of the multi-model training. But for the IXpans and the Command A, everything is completely updated, so there is no difference in terms of the embedding space as well. But my intuition is actually if you try to do something separate for embeddings, it may not help for the merging, in my opinion.